Greetings to everyone, and welcome to the guest lecture series, an initiative by Technovanza VJTI. This session is co-hosted by Gaya College of Engineering and Engineering College Ajmer. I am Mahita Sam, and I'm thrilled to be your host for today. VJTI was established in the year 1887 and is upholding its proud legacy of over a century, filled with brilliance, and has thrived in nurturing the brightest minds of our society. Taking technology to society has always been the motto of Technovanza. An ardent desire to enlighten young minds and inoculate impeccable qualities within them has been the very objective of the GLS since its inception. The eminent lineup of guest lecture series over the years has added immense value to the lives of several young minds. Pioneers of diverse fields, some of them being Dr. APJ Abdul Kalam, Mr. Ratan Tata, Professor John Maryland, Mr. John C. Mathur, and several others have graced Technovanza with their presence. Amplifying this extraordinary legacy, we are proud and elated to host the 1997 Nobel Laureate and a distinguished physicist, Dr. William Daniel Phillips. Dr. Phillips graduated from Janata College in 1970. Sir received his doctorate in physics and completed his postdoctoral research at Massachusetts Institute of Technology. In 1978, he joined the National Institute of Standards and Technology, and it was there that he conducted his award-winning research. In 1997, he won the Nobel Prize in Physics, together with Dr. Claude Cohen-Tanauji and Dr. Stephen Chu for his contributions to laser cooling, a technique to slow the movement of gaseous atoms in order to petty study them, and for his invention of the Zeeman slower. He is currently the leader of the laser cooling and trapping group at the Quantum Measurement Division of NIST's Physical Measurement Laboratory, and is a distinguished university professor at the University of Maryland. He is a fellow of the Joint Quantum Institute, a cooperative research organization of NIST and the University of Maryland that is devoted to the study of quantum coherent phenomena. In addition to this, Sir has several accolades to his name, including the Presidential Rank Award 2005, the Service to America Award 2006, and the Michelson Medal of the Franklin Institute 1996. Sir, you are truly an inspiration to the youth, and we are honored to have you grace us with your presence. Sir will be sharing his outlook on the revolutionary quantum reform of the metric system. We will be having a Q&A session at the end of the lecture, so please leave your questions in the live chat below. Sir, handing it over to you now.
Thank you very much for that, that very kind introduction. I'll share my screen now. Okay, so I'm going to be talking about the revolutionary quantum reform of the metric system, and I'm very happy to be here with you virtually at Technovanza. I am, as you heard, a member of the National Institute of Standards and Technology. This is the National Metrology Institute of the United States and is the sister organization to your National Metrology Institute of India, namely the National Physical Laboratory, or NPL. I'm also part of the University of Maryland, and together these two institutions have created a joint quantum institute where I'm doing my research at the moment. I'm, as you heard, a member of the NIST Laser Cooling and Trapping Group, and although I started that group many years ago, it is now led by group leader Gretchen Campbell and other group members, Paulette Trey Porto, Ian Spielman, Ida Tietzinger, and Charles Clark are the people with whom I work and am privileged to collaborate on a daily basis. This talk is also brought to you not just by the National Institute of Standards and Technology, but also by the International Union of Pure and Applied Physics, IUPAP. And as a member of Commission C2 of IUPAP, I am spreading the word about the reform of the modern metric system. So what exactly is the revolutionary reform of the metric system? Well, it was the French Revolution that brought us the metric system in the first place. And just recently, on the 20th of May, 2019, we have experienced the greatest revolution in that metric system since the French Revolution. And the nature of that revolution, which is a change to the international system of units, or the Système International d'Unité, or SI, as we call the modern metric system, the revolutionary change is that today, every one of the base units, the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela, every one of these base units that form the structure of the International System of Units, the SI, every one of them is now defined by fixing the value of a constant of nature. Now, in order to see how this can be done, and in order to illustrate how it was done for a different unit of measure, an earlier unit of measure, I should say, namely time, and with apologies to the late, great Stephen Hawking, I'm going to bring you my version of a brief history of time. Since we have had seconds, the second has been defined to be a certain fraction of a day. 1/24 times 60 times 60, because there are 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. So a second is 1 day divided by 86,400. Strictly speaking, a mean solar day. But ever since the beginning of the 20th century, we have known that the length of the day changes. Around that time, mechanical clocks were so good that they could tell that the rate of rotation of the Earth was not constant. And as the 20th century went on, better clocks were made. While the Earth may change its rotation speed, the ticking rate of atoms and molecules do not change, at least as far as we know. This clock that you see here in this photograph used an ammonia molecule as its ticker, and it was in fact the first atomic clock in 1949. Later, the National Physical Laboratory in Great Britain, 1955, made the first cesium clock, and operated this cesium clock as a clock that was easily better than the rotation of the Earth in terms of its stability and accuracy. And so in 1960, faced with a situation where a technology existed that could measure time far better than the standard of time, could define what we mean by 1 second, it was time to redefine the second. And so they did redefine the second to be a fraction of the year 1900. What were they thinking? This must have been the stupidest decision that has ever been made in the history of metrology, to define the second in terms of a fraction of the year 1900. It's true that the length of the year 1900 never changes, but it's not exactly easy to access the year 1900 as a standard of measurement. Astronomers do a very good job of extrapolating backwards, but nevertheless, it's not a very convenient standard. And so finally, in the years 1967 and 1968, the General Conference on Weights and Measures adopted a new definition of time, an atomic definition of time, that said that the second is the duration of a certain number of periods of the radiation corresponding to the transition between two energy levels in the cesium atom. About 9 billion ticks of the cesium atom corresponds to 1 second. And I want to emphasize that this is very much in the spirit of the modern changes that I'm going to be telling you about, in that it is a quantum standard. The energy levels of cesium are the result of quantum mechanics. And quantum mechanics also guarantees that this frequency difference between energy levels is going to be the same for all cesium-133 atoms everywhere in the universe, as far as we know. And ever since that definition was instituted in 1960, the quality of these cesium clocks has been getting better and better. It was about a part in 10 to the 11th at the time that the definition was changed. And by the year 1990 or so, the quality had gotten to be better than a part in 10 to the 14. But in fact, it wasn't getting any better than a part in 10 to the 14. Why was that? Here's a picture of a clock at NIST that achieved that kind of accuracy, better than a part in 10 to the 14, but it didn't do better than a part in 10 to the 14, much better than a part in 10 to the 14, because of the motion of the cesium atoms. The thermal motion of the cesium atoms, they're moving faster than 100 meters per second, which meant that they didn't stay in the apparatus for very long. There was a Doppler shift, a huge Doppler shift on the order of a fraction of a part in 10 to the 6th. There was a relativistic time shift on the order of some parts in 10 to the 13. And these all limited the performance of these kinds of clocks. It was laser cooling, which, as you heard in the introduction, I've had something to do with, that addressed this problem. It made the cesium atoms move much more slowly, and it allowed clocks to be so improved that they're good now to a few parts in 10 to the 16. Here's a photograph of one of those clocks in our laboratories at NIST. Don Meekhoff and Steve Jeffords cool cesium atoms down here. They launch them up about a meter high. They come back down after about a second, and clocks like this keep time to a few parts in 10 to the 16. It is the most accurately measured quantity in the International System of Units. So I want to emphasize what the key idea here was. We started with a definition of time that was based on the rotation of the Earth. There's nothing special about the rotation of the Earth, and there's nothing that guarantees that it will be constant. In fact, we know very well that it is not constant, that it changes because of the friction of the tides, because of changes in ocean currents, because of earthquakes. And so because of this changeability of this arbitrary artifact, and because of the arbitrary nature of it, we change to a quantum definition having to do with the frequency corresponding to a transition in some particular atom, in this case, atoms of cesium. Now, I want to tell you another story, a short history of length. Length was a really important unit of measure historically because it involved commerce. And the most ancient ways of handling length was to use the human body as a standard of length. The cubit, for example, was the distance between the elbow and the fingertips. And this was extremely convenient because you always had your units of measure with you. The trouble was it was not very consistent because a short fabric merchant might be selling you a smaller length of fabric than you had expected. And so, in order to address this problem, one of the ways in ancient times was to use a particular body, not just the human body of the person who was selling you fabric, but a particular body. For example, the body of the monarch. In ancient Egypt, it was the body of the pharaoh, and the pharaoh's arm set the length of the royal cubit. And this was used in order to do things like build the pyramids. But of course, they realized also that using the pharaoh's forearm, while it was consistent, it was not convenient. And so they made an artifact, and there's a picture of it here, this granite cubit was the standard of length for Egypt at the time, based on the size of the pharaoh's forearm. And secondary standards made out of wood were calibrated against this granite standard, and they were used out in the field to do things like build the pyramids. And the people were very serious about their metrology because the penalty for not calibrating your wooden cubit against the granite cubit was the penalty of death. And as a result, of taking metrology so seriously, the pyramids were made to incredible accuracy. The baselines of the pyramid were consistent to a small fraction of a percent. They were square to 12 arc seconds of angle. They were really well done because of the seriousness of the metrology. But this idea of having an artifact to set the standard of length was something that was carried out in many places all over the world. In Europe, for example, you had an artifact, which often were different from one town to the next, that provided the standard of measurement for that town. Here is a photograph of the standard fathom, nominally the wingspan of the arm span of a human being. But as you can see, here in this town, the town of Regensburg, the fathom is quite long. So this looks like a really good place to buy fabric. But if you went into surrounding towns, there would be a different standard of length. So this was a common problem, but a truly annoying problem, that you could have a standard of length that would be good for the town in which you lived, but if you moved to a different town, you'd be dealing with a different standard of length. So at the time of the French Revolution, the revolutionary thinkers decided they would solve this problem, that they would create a standard of measurement. The meter would be the new standard of measurement for length, and it would become the measure of all things, and it would be available to everybody. And they decided that in order to meet this ideal of having a standard of length that was available to everyone, they would define the meter in terms of the Earth itself. It sounds familiar. The second was already defined in terms of the rotation of the Earth, and now they were going to define the meter in terms of the size of the Earth. So a meter was defined to be 1/10,000,000th of the length of a meridian going from the North Pole to the equator on a meridian that goes through Paris. And so in order to relate this new definition of the standard of length, the meter, to the old definitions, they created a team of surveyors who surveyed the distance between Barcelona here in Spain and Dunkirk here in France. In terms of the old units, they came back, and because, well, first of all, let me say that this idea was to provide something that would be good for all time and for all people. And they created this medal that you see here. It shows a mythological creature actually measuring the Earth. That's what they did with these surveyors who went out into the field to measure the length of a small portion of this meridian and then extrapolate it to the full meridian. But what they found was that while this was a wonderful idea in principle, that using the Earth as a standard was not something you could easily go back to. They measured it once, and then they created an artifact standard again, just as the ancient Egyptians had done after comparing to the pharaoh's forearm. They made an artifact standard. The French revolutionaries did the same thing. And here is a photograph of the meter of the archives. It was deposited in the archives of France in 1799 and became the standard of length for the entire country in 1799 at the end of the 18th century. Very much in the spirit of the Egyptian cubit, and it was an artifact, something that one would need to come to calibrate other standards. It was defined to be the distance between one end and the other end of this meter stick. But if you think about it, in order to measure an end standard like this, you have to touch the end, and that meant that it could become worn, and so it might change with time. And so some decades later, when there was an international meeting in order to adopt the metric system for the entire world, it was agreed that this end standard, the kilogram of the archives, would be replaced with a new standard, a line standard. So the meter was the distance between two scratches on a platinum iridium bar. And this became the new artifact, the new standard that defined what was meant by a meter, now not just for France, but for the entire world. And this was called the International Prototype of the Meter. But almost as soon as this new meter was made, it became clear that there were better ways of measuring length than using such an artifact that was the distance between two scratches. They had discovered in the 19th century that light was a wave. And they made instruments called interferometers that allowed them to interfere waves of light. This is a cartoon of a kind of interferometer called a Michelson interferometer. The idea is that light comes along here. It hits a beam splitter that allows some of the light to be transmitted and some of the light to be reflected. The light that is transmitted goes to another mirror that reflects the light back, and some of that light reflects from the beam splitter and goes to this detector. The part that's reflected from the beam splitter goes to this movable mirror. It comes back and interferes with the light that went to the other mirror on this detector. And when the interference is destructive at the center of this pattern, you get a dark spot. But if you move this movable mirror by just 1/4 of the wavelength of light, and the wavelength of light is less than 1/1,000,000th of a meter, so you move this mirror by just 1/4 of the wavelength of light, it changes this dark spot to a bright spot. So that means that it's easy to measure the length by which you move this mirror to a small fraction of the wavelength of light. Whereas to measure the distance between two scratches, the scratches are many millionths of a meter wide, and it's very difficult to tell where the middle of the scratch is. So that meant that the definition of the meter was much worse than the ability of people to measure length itself. So it's just like the situation we had with time when we had atomic clocks that were better than the definition of time itself. You had to change the definition of length. And that was done rather late in the year 1960, the year the laser was invented. They decided to define the meter in terms of a certain number of wavelengths of the light from a krypton lamp. And here's a picture of that krypton lamp. And that became the new definition of the SI meter, the meter in the International System of Units. But almost as soon as that definition was made, people discovered that the purity of the light from this krypton lamp was not as good as the purity of light from lasers, which were now becoming more and more common, and that people could measure length using laser light much better than they could measure length using light from a krypton lamp, because the light from the laser was so much more pure. And so people began to use, I just want to, before I mention what people started to do, I just want to mention that, again, as in the case of time, that we had now a quantum length standard. The energy levels in krypton atoms that define the frequency and therefore the wavelength of the light emitted by the krypton are fixed by quantum mechanics, which also guarantees that the wavelength of all krypton atoms is going to be the same. And so this is a quantum standard of length. But now we had lasers, and lasers are also quantum standards of length. This particular laser that you see here is a helium neon laser. It's locked, its wavelength is locked to a transition in molecular iodine, and people all over the world began using these lasers as de facto standards of length, just as people had been using lamps as de facto standards of length in the early part of the 20th century. So what it meant was people were using these things as standards of length, but the length that they were measuring was not in SI meters because the meter was defined in terms of krypton. So it was clear that what we needed to do was to redefine the meter again. The obvious choice would have been to define the meter in terms of an iodine stabilized helium neon laser. But fortunately, they did not do the obvious thing. They did something far more brilliant than the most obvious thing. They defined the speed of light. Why does that give you a length standard? Look at this equation. The wavelength of light times the frequency of light is equal to the speed of light. And this is true regardless of what the wavelength of the frequency is, that the product of the wavelength times the frequency is always equal to the speed of light. If we define what we want the speed of light to be, and if we measure its frequency in terms of the new definition of the second, that means we automatically know its wavelength, regardless of where the light came from. It could be laser light, it could be some new kind of laser instead of a helium neon laser. And so if people make better lasers, and they did, the definition is still good. If people make better ways of measuring frequency of light, and they did, the definition is still good. So in 1983, the definition of the meter became the length of path traveled by light in vacuum during a certain fraction of a second. And that definition effectively defines the speed of light. The beauty of this is that not only does it take an artifact and define it in terms of an atomic constant, it in fact defines a fundamental constant of nature so that we are not tied to any particular atom the way we are with the definition of time. We're depending upon a universal constant of nature, the speed of light. And the beauty of this is that we should never have to change the definition again. Improvements in the technology will be welcomed and will be used in this current definition. And now, this beautiful approach to defining a unit, in this case, the meter, this beautiful approach to defining the meter by defining a fundamental constant of nature, we are now going to bring that brilliance and beauty to the definition of the kilogram, as well as to the ampere, the Kelvin, and the mole. And this new definition went into effect on the 20th of May, 2019. Why was it necessary to do this, and how was it done? Well, in order to explain that, I'm going to give you a light history of mass. In ancient times, as with so many other things, there were artifacts. This set of polished stones was used in ancient Babylonia as the mass standard. If you went to a different place, for example, if you were in India, there would be a different mass standard. And here we can see this balance where the emperor is weighing his son in terms of the mass standards that are being put on the other side of the balance. At the time of the French Revolution, the revolutionary thinkers believed that they should come up with something that would be universal. And remember, they had thought of the meter as being the measure of all things. And so they came up with the standard of mass, a new unit of mass called the kilogram, which was based upon the meter. It was the mass of 1 cubic decimeter of water. A cube of water, 1/10 of a meter on a side, should have a weight of 1 kilogram. Well, this was wonderful. Water was something that was easily available. We had this new definition of the meter. The trouble was that it wasn't so easy to determine what a kilogram was using this definition, as wonderfully universal as it might seem. The density of water changes with temperature. It's not that easy to get exactly 1 liter of water. The water sticks to surfaces differently depending upon the nature of the surfaces. For some surfaces, the water may stick. For other surfaces, the water may not wet the surface and be repelled. And this changes the way in which you make measurements. And so, in the same spirit that we've seen so often in history, they made an artifact. And here is that artifact. I'm holding it, or I'm holding the box that contains the artifact. This is the kilogram of the archives. They made a platinum cylinder to be equal as close as they could determine to the mass of 1 liter of water. And then this became the standard of length for France in the 18th century. And in 1799, just as with the meter of the archives, they deposited the kilogram of the archives. And I'm standing here in the archives of France holding that kilogram of the archives. Well, some decades later, when we had the international agreement, the International Treaty of the Meter, where the countries of the world agreed to adopt the metric system as an international system of measurement, a new standard was ordained, made out of platinum iridium, and the international prototype of the kilogram is shown here under 3 bell jars to protect it from the environment. And it was made to be as close as possible to the kilogram of the archives. And this was and remained the standard of length, the standard of mass for the entire world until the 20th of May, 2019. Here's a picture of me at the 125th anniversary of the International Treaty of the Meter. The kilogram is right here under all these bell jars. And this is at the International Bureau of Weights and Measures outside of Paris. So think about this. Up until less than 2 years ago, the kilogram was defined by this definition. The kilogram is the unit of mass. It is equal to the mass of the international prototype of the kilogram. We were in the 21st century, and the unit of mass was an artifact, an actual piece of metal that was made in the 19th century. It was based on an object made in the 18th century. The fact that this could be true in the 21st century was so scandalous that an American newspaper comic strip was making fun of it. Here's the comic strip. In this comic strip, it begins with a little girl who's going to school in this school building, asking her science teacher, isn't it true that we've redefined the meter to be the distance traveled by light in a certain fraction of a second? And the science teacher says yes, because the previous definition that was based on the dimensions of the Earth was inaccurate, as we've seen. And she says, and haven't we also redefined the second, which used to be a fraction of a solar day, to be a certain number of oscillations of a cesium atom? The science teacher says, yes, very good. And then she says, so why haven't we changed the definition of the kilogram? He says, we haven't? No, the official definition is still the mass of the international prototype of the kilogram, an actual lump of stuff that's stored somewhere. What if someone sneaked in and shaved off a piece? This so upsets the science teacher that he has to lie down. And we learned that the little girl was just trying to get him bothered. And she has succeeded. But even though no one has indeed sneaked in and shaved off a piece of the international prototype of the kilogram, it appears that its mass is indeed changing. This plot shows the mass of a number of copies of the kilogram, copies that were made at the same time that the international prototype of the kilogram was made. In fact, the international prototype of the kilogram was chosen among all of these copies because it was the one that was closest in mass to the kilogram of the archives. And what you see is that over many decades, that the mass of these other copies of the kilogram are getting larger compared to the kilogram. Well, if you imagine that all of these copies, which were made to be exactly the same, as far as anybody could tell, appear to be getting heavier, then maybe what's happening is that the actual international prototype of the kilogram is getting lighter. But of course, it cannot get lighter because legally, it is always, by definition, it is always a kilogram. Well, this is an intolerable situation. And we have to fix this problem. And in order to fix it, we want to do the same thing as we did with the meter. We want to define some constant of nature. With the meter, it was the speed of light. What constant will we use for the kilogram? Well, in order to understand that, let's recall for a moment the most famous equation in history, E equals mc squared, that the energy of an object at rest is equal to the rest mass of the object times the speed of light. Now let's look at another equation, not quite as famous. It says that the energy of a photon, a particle of light, is equal to Planck's constant times the frequency of the light. In fact, this is how we define what we mean by Planck's constant. And we measure it by measure the frequency of the light, and measuring the energy of the light, we can measure Planck's constant. Let's combine those two equations and solve for the mass. We find that the mass is equal to Planck's constant times the frequency divided by the speed of light squared. What does this mean? What it means is that if you had some particle, let's say an atomic nucleus, and it emitted a photon, let's say a gamma ray of a certain frequency, f, then if you know what Planck's constant is, that is, if you fix its value by defining it, and we've already defined the speed of light, if you can measure the frequency in terms of our definition of the second, then you know what the mass is. Now, we don't actually do it this way. We don't measure the mass of photons in this way. We could, but we can't do it well enough for the demands of mass metrology. This is just to give you an idea of why defining Planck's constant allows you to define the unit of mass. But there is another way. Due to this man, Brian Kibble, he invented an electromechanical device, which we now call a Kibble balance or a Watt balance. And let me show you a movie now that describes how that Watt balance works. So here we go. So now I want to invite you to remember how we measure mass traditionally. If we have an unknown mass, let's say here on this side of the balance, in order to measure its mass, we put known masses on the other side of the balance. And when the balance is balanced, then we know that the known masses on this side of the balance equal the unknown mass on this side of the balance, and that's how we've always measured mass. Now I want to invite you to think about a different way of measuring mass. Let's imagine that on this side of the balance, we have a coil of wire. And we put current in that coil of wire. And we also have some magnets that create a magnetic field. And the current in this wire experiences a force in the presence of this magnetic field. And if we can measure the current in the wire, and if we know where the wire is and where the current in the wire goes, and if we can measure all of these magnetic fields everywhere around where the wire is and the direction of the magnetic field, we could calculate what the electromagnetic force is. And if we know the acceleration of gravity, then we can determine what the mass is. But We cannot know those things. We cannot measure where all the coils are in this wire. We cannot measure the magnetic field and its direction to the accuracy that we need. And here's where the genius of Kibble comes in. What Kibble said was, let's take this coil of wire. Let's take the ends of this coil, open it up, and connect it to a voltmeter. And now, when we move the coil in the presence of the magnetic field, it generates a voltage. And if we measure that voltage, and if we measure the velocity of this coil in what we call the velocity mode of the experiment, we will get from that measurement all the information we need about the geometry, about the strength of the magnetic field and the geometry of the coil. And you'll see why in a moment. And so we make that measurement in velocity mode, the velocity of the coil and the voltage that's generated when we move the coil at that velocity. And we do the other part of the experiment, what we call the weighing mode, where, just as we've mentioned before, we put current into the coil of wire and we use that current to balance the force of the mass on the other side of the balance. That's the essence of the Kibble balance. So why does it work? Because the mass on one side of the balance, the unknown mass times the acceleration of gravity, times the velocity. This is a force times a velocity. That's power, mechanical power. That has got to be equal to the current from the weighing mode times the voltage from the velocity mode. That's electrical power. Now look at this equation. On one side, we have the current from the weighing mode, the voltage from the velocity mode. On the other side, we have the mass from the weighing mode and the velocity from the velocity mode. And the two things together have to be equal because mechanical power is equal to electrical power in a good system of units. And so if we solve for the mass, we see that we can determine the mass by measuring the current and the voltage, the acceleration of gravity, and the velocity. But you may remember that I promised you that we were going to get mass by defining Planck's constant. So how does that work? Well, it works because of the way in which we can measure the current and the voltage. We have the quantum Hall effect from Klaus von Klitzing, the Josephson effect from Brian Josephson. Here they are. There's Brian Josephson. There's Klaus von Klitzing. And they taught us that that a superconducting circuit produces a voltage when there's a certain frequency, or better still, that a certain voltage across a superconducting element called a Josephson junction produces a frequency that is determined by the constant 2E/h in hertz per volt. Whereas von Klitzing told us that a resistance, a cross resistance in a semiconductor device produces a standard resistance in ohms of h/e squared. So both of these quantities have E and H in them. And so when we measure voltage in units of h/2E, and we measure current, which is voltage, which is 2E/h, times divided by resistance, which is h/e squared, then when we see that the Planck's constant cancels out and the current is related to the charge on the electron, so that cancels the charge on the electron over here, and mass is proportional to Planck's constant, just as I promised you. And these balances, here's a photograph of one of those balances at NIST, can realize the kilogram to an accuracy of about a part in 10 to the 8th, which is better than the kilograms are changing due to whatever it is which we haven't been able to figure out. I'm just calling it dirt. And the people who did this experiment are so serious about their metrology that they have tattooed the values of the fundamental constants into their arms because they're so confident in the nature of the metrology. Now, the beauty of defining the kilogram by defining a value of Planck's constant is that we are not tied to one particular way of realizing the definition of the kilogram. Here is another way. Imagine an atom at rest that has certain energy levels that can be excited by sending in photons from a laser. So you send in a photon of the right energy, which is to say it has the right frequency, because we're going to define Planck's constant. It also has a certain momentum, which is Planck's constant divided by its wavelength. So when the atom absorbs that photon, the atom will go from some lower energy level to some higher energy level, illustrated here, absorbing the energy. And because of the momentum, the atom will be moving with a velocity that's equal to Planck's constant divided by the mass times the wavelength of light. If we measure that velocity, if we measure the wavelength of the light, we can solve for the mass, and we've determined the mass of this atom in kilograms, assuming that we've defined Planck's constant. If we've got the mass of some atom in terms of kilograms, we can compare it to the mass of other atoms. There are mass comparators, ion traps, that allow us to do a very accurate job of, say, comparing the mass of this atom, it might be rubidium, to the mass of some other atom, like silicon. And then, if we make a sphere of single crystal silicon, and we measure the lattice constant, the spacing between the atoms in that sphere of silicon, we can, and then measure the size of that sphere, we can essentially count the number of atoms in that sphere. And since we know the mass of one atom, we now know the mass of this sphere. And that's another way of realizing the kilogram by defining Planck's constant. And this has been done in the German National Standards Laboratory and in other laboratories around the world. And here is a map showing where national laboratories all over the world, including at NPL in India and at PTB in Germany and in other places around the world, have used both of these methods to measure first Planck's constant, because before you've defined Planck's constant, this experiment is essentially measuring Planck's constant. And once everyone agreed on Planck's constant, then finally they changed the definition of the kilogram. But that's not all. The ampere used to be the current which, when put into two infinitely long straight wires 1 meter apart, would produce a force of 2 × 10⁻⁷ newtons per meter. That is no longer the case. Under the new SI, the ampere is a current of a certain number of electrons per second, because we have defined the charge of the electron in coulombs. Now, one of the most beautiful things about this is that now that both E and H are defined, that means that the Josephson constant and the von Klitzing constant are both defined. And that means that the definitions of voltage and resistance are exact in the International System of Units. Why is this important? Because since 1990, there was a separate set of units for electrical measurements based on fixed values of the Josephson constant and the von Klitzing constant. The international community decided to fix the values of those two constants. They were not fixed by the International System of Units. They were chosen to be as close as possible to their measured values in the International System of Units, but they were not exactly in the International System of Units. That meant we had two different systems for measuring electrical quantities: the International System of Units and the legal or practical system of units, in which 2E/h and h/e² were exactly defined. Now, in the new SI, where H is defined in the SI and E is defined in the SI, that means that 2E/h and h/e² are both defined in the SI. And now the legal or practical definitions for electrical units are now the same as the SI definitions, so we no longer have a double standard. And that means we can measure voltage and current in the SI using these exact values. In addition, we've also changed the definition of the mole, which used to be the number of carbon-12 atoms and 12 atoms of carbon-12. Now it's simply a number. In other words, we have defined the Avogadro constant. And finally, the Kelvin. It used to be 1 over 273.16 of the triple point of water. Now we've defined the Boltzmann constant. So that means that the Kelvin defines an atomic concept, the thermal energy of the atoms and molecules that make up the substance of which we're measuring the temperature. By defining the Boltzmann constant, we define the temperature scale in terms of that atomic energy. So the French Revolution brought us the metric system with meters as the measure of length, as the measure of all things, also of kilograms as the measure of mass. The Convention du Mètre, the International Treaty of the Meter, brought us an international agreement so that the entire world was agreeing on the system of units. And finally, on May 20th of 2019, the anniversary of the signing of the 1875 Treaty of the Meter, we had another revolution in measurement, the biggest revolution since the French Revolution, that defined the units of measure in terms of constants of nature. And what that means is that in the revolutionary spirit of liberty, we now have a measurement system that is free of artifact standards of measurement, and it's free of this double standard for electrical measurements, that the SI and the legal amperes are finally the same. So all the base units are now defined by fixing values of constants of nature. The entire international system of units can be written down on a wallet card that you can carry in your pocket. And it seems that we have really done what the French revolutionaries dreamed of. Excuse me, that we have created a system of measurements that really is good for all times and for all peoples, as this medal indicated. And so the decision that this should be done was made in advance of the actual implementation of the change in December of 2018 in the city of Versailles, outside of Paris in France. The General Conference of Weights and Measures decided that they would adopt this new definition. And after the vote of 60 countries present at the time, they showed this movie. 60 countries agreed.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world scientific community.
At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it.
Ce l'abbiamo fatta. Vi har det geschafft.
Lo logramos.
Lacey Aboli.
我们做到了。
Biz buna nail olduk.
Proud om daar.
We worden жасадық. Het is ons gelukt.
We сделали это.
Fantastiskt.
Vi gjorde det.
Amerika.
Mi smo to učinili.
Dokázali jsme to.
سويناها.
Congratulations. 축하합니다. Felicitaciones.
Mazal tov.
Congratulazioni.
Shatter le lavorisce.
Summer success.
Parabéns.
Ongela. Momento.
Am guida.
Onneksi olkoon.
Mabruk.
Kapai.
Anniko.
Félicitations. Congratulations.
So the fact that we have now a system of units that really is for all time, for all people, and the fact that the international community of metrology, 60 countries of the world, could agree unanimously on this change really gives one hope for the future, and this really satisfying idea that we have something that's good for all times and for all people. But do we really? What about time itself? What about the second? You see, the second is defined in terms of the oscillations of a cesium atom. The problem with this is that it's not a fundamental constant. It is a particular atom. And as we've seen, this atom is wonderful. It allows the most accurate measurements of anything there is to a few parts in 10 to the 16 using this cesium atom with atoms cooled below 1/1,000,000th of a degree above absolute zero. But today, we have found other atoms. Junyi and his colleague Anna Maria Ray have used strontium atoms to produce a clock that is 100 times better than the cesium clock. Dave Wineland, using a single aluminum ion, has gotten an accuracy even better than a part in 10 to the 18 of 9.5 parts in 10 to the 19. Almost an unimaginable accuracy. But what it means is that, as we have seen again and again in the history of metrology, we have a better technology, a technology that can measure time, that can measure frequency better than the very definition of time itself using a cesium atom. And so we are at a kind of crossroads, as we have been often in the past, where we needed to change the definition of time, of length, or of mass, that again, it appears that we need to change the definition of time. And there are a whole range of possible atoms that are creating time standards better than cesium. These are time standards where the frequency involved is an optical frequency, thousands of times higher than the microwave frequency at which the cesium atom clocks operate. And they are ions and they are neutral atoms, bosons and fermions. Each of them have their advantages. And we don't yet know which one of these will be chosen, but we do know that some kind of a reform in time is going to be necessary. And so it appears that time is always going to be a problem, because when we finally do decide on a new definition of time, it will again be some particular atom. It will not be a fundamental constant of nature. And so it may be that we always will have the problem that time itself will be the one thing that is not good for all times. And so we come to the end of this talk, but it really is not the end, because the SI second still needs to be defined. Thank you very much.
Thank you, sir, for the truly insightful lecture.
Wonderful, Dr. William. Wonderful.
I'm sure that I'm speaking on behalf of the entire audience watching us right now, that you have enlightened us with extensive knowledge and promising ideas while instilling a new perspective in our lives. Before we conclude, there are a few questions that we would like to ask you. Can I start with the first question, sir?
Yes, please.
How can quantum physics revolutionize the way of our learning, and how can it help humanity grow or develop?
Well, I would say that quantum physics has already helped humanity in any number of ways. Let's talk about the most practical ones. Almost everything that we consider to be part of our modern technology, the kinds of things that define the way in which we live our lives in a modern era. For example, the computers and smartphones on which people are watching this lecture, the thing that allows you and me to communicate over half of the of the size of the Earth. These all depend on quantum mechanics. We wouldn't have computers. We wouldn't have any semiconductor electronics without having understood quantum mechanics. It was only the fact that we understood quantum mechanics that allowed people to develop things like transistors and integrated circuits, that allowed us to develop things like the global positioning system, that allows us to navigate, that allows us to find our way around unfamiliar places. So quantum mechanics has already been something that has had a huge influence on our daily lives in a very practical way. We all have in our homes, not just the computers on which we do things like see remote lectures, but there are computers built into most of the appliances that we have in our homes these days. So quantum mechanics is almost ubiquitous. In addition, some people might say that understanding quantum mechanics has given us a different way of thinking about life philosophically. That quantum mechanics is based on ideas that include the Heisenberg uncertainty principle, the idea that it is not possible to know accurately, with perfect accuracy, both the momentum and the position of a particle, or the energy and the time at which you would measure the energy of something. These things cannot simultaneously be known with perfect precision, that there is always a fundamental and irreducible uncertainty in these things. Some people believe that this is a useful philosophical insight, that in life we're always faced with a certain degree of uncertainty that we can never remove. You can decide for yourself whether you think this is a useful philosophical insight, but a lot of people believe that as well. There's a phenomenon in quantum mechanics called entanglement, which tells us that the nature of objects can be connected to other objects that are quite remote. And this is another philosophical insight that we get, that some people believe is an important insight from science that might be applied to our philosophical understanding of life, having to do with the unity of all of nature. So those are two of the ways in which quantum mechanics has influenced our lives.
Yes, so that's truly a great outlook on quantum physics and mechanics. So moving on to the next question. How will the reform in the metric system affect measurements and calibrations made in everyday life?
Yes. So most things of everyday life will not be affected. In fact, if we have done our job correctly, there should be a continuity between the old ways of doing things and the new ways of doing things. In the old way, for example, the kilogram, the international prototype of the kilogram, was exactly 1 kilogram. In the new system, the international prototype of the kilogram is no longer exactly 1 kilogram. It's something we can measure, and we have. We've been measuring it, and under the new system, it's about 1 microgram different from a kilogram. But on the uncertainty in measuring it is more than 1 microgram, so effectively nothing has changed. But as we go on, this new way of measuring mass using a Kibble balance is going to have some useful effects. One thing is we no longer have to worry that the standard of mass is changing. So we no longer have to worry that when we measure the mass of something, that if we measure it again, we don't have to worry about whether we get a different answer is because the standard of mass was changing or because the object itself changed. Now we can know whether the mass of things is stable or not. But it's even better than that. It turns out that measuring really small masses is going to be much better, much easier and more accurate under the new system. Why is this so? Well, imagine that I need to make a small standard of mass. Let's say I want to measure something that's only a milligram. How do I get a 1 milligram standard? Well, the standard that I have is a kilogram. So one of the ways I could imagine getting a smaller mass is I make 10 100-gram masses. And I take all of those 100-gram masses and I compare them to the 1 kilogram. This way I can make the sum of all those 100-gram masses to be exactly 1 kilogram. And then I can compare each of them to each other and find out how much each of them is different and figure out how each of them is different from 100 grams. Then once I have a 100-gram standard, I can make 10 10-gram standards and do the same thing, going all the way down to a milligram. By the time you get down to a milligram, you have introduced so much uncertainty because of this process of dividing up that you've lost a great deal of the accuracy that you had to begin with. We don't lose that accuracy in the new way of doing things. In the new way of doing things, we don't have to start with a kilogram. We just make a kibble balance to measure 1 milligram, and we can make that measurement as accurately as we can make any kind of measurements. We don't have to worry about a standard that has lost accuracy because of this subdivision. The accuracy is maintained. So that may be one of the biggest benefits from a practical point of view, that small masses will be more accurate.
So that's quite fascinating. So the next question that we have for you is, how did you develop an early interest in physics and what inspired you to take up research?
Well, I think that every child is born with a natural curiosity. When I go into a school and talk to children who are in kindergarten, 5-year-old children, they are interested in absolutely everything. It doesn't matter what sort of a demonstration I do for 5-year-old children, they are absolutely enthralled by anything that looks new, and they want to learn everything they can about it. One of the things I like to do when making demonstrations is to use liquid nitrogen, an extremely cold liquid that boils when you pour it on the floor, because the floor is so hot compared to the liquid nitrogen, it makes it boil. When I give a talk to a group of adults and I pour liquid nitrogen somewhere close to where the adults are sitting, they all recoil back and try to avoid this stuff because it seems frightening. If I do that with a room full of kindergartners, they are all on their hands and knees trying to see what this wonderful stuff is. That natural curiosity is something that I think is part of every child. So when I was young, I had that natural curiosity, and my parents encouraged that curiosity. And I think that scientists in general, not just physicists, but scientists in general, are simply people who have never grown out of that natural curiosity. My parents fed my curiosity by, for example, giving me a microscope, by buying me a chemistry set, by helping me build a laboratory in the basement where I could do experiments. So they fed that curiosity. And so I think that it was a combination of the natural curiosity and the fact that my parents, who interestingly were not scientists, but they fed this natural curiosity of mine. Now, some people might also ask, well, okay, why physics? Well, I don't really know for sure. I give a couple of answers which are sort of like jokes. I don't have a very good memory. And my memory is getting worse and worse as I get older and older. And in biology, you had to memorize a lot of things. You had to memorize the names of and the classification of all sorts of animals and plants. And in chemistry, you had to memorize what different chemicals would do when you put them together, how they would react. But in physics, all you had to do was know a few basic equations, and everything else could be figured out. So I didn't have to have a good memory in order to do physics. I only had to remember a few equations and know how to do mathematics. And for me, that was a lot easier because I don't have a good memory. Another sort of joke is to say, well, you know, chemistry is smelly and biology is icky, but physics is nice and clean. And so that made physics more attractive to me. But all these are really just jokes. I think it's just a matter of personal taste that that I liked physics more than I liked the other sciences. But look, I am still fascinated by all the things that I read about that are happening with biology and chemistry and astronomy and geology and all of the sciences I find still to be fascinating. But physics is the thing that I've made my career on.
Yes, sir, and I would really like to say that your journey is truly inspiring for all of us. So moving on to the next question. You are one of the very few scientists who have been involved in the science and religion dialogue. Could you please elaborate on that?
Okay, well, first of all, while it might be true that I'm one of the few scientists who's been involved in the dialogue of science and religion, I don't believe at all that there's anything special about me as a scientist who also is a person of religious faith. When I talk, I mean, the trouble is that most of the time when I get together with other scientists, we're talking about science because that's what we do. We just love to get together and talk about science. Occasionally, the issue of religion comes up. And what I find is that most of the scientists that I talk to have some kind of religious faith. It may not always be like mine. It may not always be like yours. It may not always be the most conventional kind of religious faith, although I think my own is fairly conventional. But I would say that most of them have some kind of religious faith. Take somebody like Einstein. Einstein said that he did not believe in a personal God, but he talked about God all the time. He said, I don't believe that God plays at dice with the universe. When he was figuring out his theory of general relativity, he said, I thought that I was getting a glimpse of what the old man was thinking. So it's funny that he would say that he didn't believe in a personal God, but he talked about God in a very personal way. He said that he believed in the same way that Spinoza did, that God was a kind of embodiment of the order and unity of the universe, of the beauty that one sees when one looks at the whole universe, and I think a lot of scientists see it that way. So I will count Einstein as being someone who is a person of religious faith. It's just not necessarily the conventional religious faith that a lot of organized religions would agree upon. So. So I would say I'm not really sure. So tell me what the question was again.
Could you just elaborate on the science and religion dialogue?
Okay.
That was the question.
So first of all, I think one of the things that's important is what I've just said. A lot of people think that most scientists are atheists, that they don't believe in any kind of divine entities, and I don't think that's true. I think that's just a wrong idea. I think that if you include the breadth of belief that scientists have, that at least some bare majority of scientists would say that they have some kind of belief in God. I think that also one of the misconceptions that there is that somehow science and religious faith are necessarily opposed to each other. Well, the fact that a large number of scientists, a large fraction of scientists have some kind of religious faith, I think tells you just by example that this isn't true. But I think that it's probably useful to look into why it is that people believe that there is this conflict between religion and science. And I think that, well, there's a number of reasons why there's been this misconception. But I think that one of the problems is for why this misconception has developed is that people make the mistake of asking the wrong question to the wrong discipline. If I want to ask a question like, how should I behave personally? What should be my attitude toward the way I behave to my fellow human beings? How should I think about my responsibilities to take care of the earth? These are questions that I think are well posed to put to the area of religion and maybe ethics as well. If I want to ask, how could I best affect the environment? That is, what could I do in order to prevent the earth from warming up? Well, I'm going to look to science for that kind of a question. Whether I should do that, maybe I should look to religion for that question. If I want to know how can I create some medical treatment that will help people who are sick, I'm going to look to science to how to do that. If I want to ask the question, should I help people who are on the other side of the earth, whom I don't know? Should I devote time and money in order to help them? I should look to religion for answering questions like that. So I think that a lot of time that the apparent conflicts that people see come from putting the important questions to the wrong discipline.
That's a very interesting perspective on the science and religion dialogue. So the last question that we have for you is, in your doctoral thesis, you measured the magnetic moment of proton in water. And to date, yours is the most accurate determination. How did you pursue this?
How did
you pursue this?
Oh, how did I pursue it? Well, for that, I have to thank my thesis advisor. My thesis advisor was Dan Klepner, a wonderful man. I still go to him when I want advice about tricky problems. He's such a wonderful and wise person. And he realized that this was an important measurement to make. So that's the first thing. And so he presented it to me as an important problem. And he had a good idea for how it should be done. He was one of the inventors of a device called the hydrogen maser. You may have heard of masers. They're basically lasers, but for microwaves instead of for light. They were developed before lasers, and the word laser sort of came about as a modification of the word maser, which stands for microwave amplification by stimulated emission of radiation. Well, he was one of the inventors of the hydrogen maser, and he realized that you could use a hydrogen maser as a very accurate way of measuring a magnetic field using the magnetic moment of the electron in the hydrogen atoms. And then he realized that if in exactly the same magnetic field you put some water, you could measure the frequency of precession, because that's what happens to the magnetic moment of of the protons in water, they precess in a magnetic field as they go around like that. That frequency of precession is a measure of the strength of the magnetic moment. So you could measure that in exactly the same magnetic field. So by first measuring the electron precession and then measuring the nuclear precession, the protons precession, you could measure their ratio. And that was the key thing. That was what we were trying to do, was that ratio. The magnetic moment of the proton and water in Bohr magnetons is essentially measuring the ratio of the precession frequency of protons to the precession frequency of electrons. So he had this idea that this was how it could be done, and he had a really great magnet. It was a very uniform field. So then it was my job to figure out how to take this vision that he had and turn it into an experiment that actually worked. And so I had to develop a system where there could be both a maser and water and the maser has to be in a vacuum, and the water obviously isn't in a vacuum, and how we could do this. And so, it took me a few years to figure out all the ways of making that work. And so I think that's the way it works for almost every thesis, an experimental thesis. You have a thesis advisor who has a vision, and you have a student who has to come up with ways of bringing that vision into reality.
So that's quite interesting. Thank you for the impactful and thought-provoking session. We hope you all enjoyed the session. I'm Manita Samant signing off. Until next time, this is Technovanza VJTI.
Thank you very much. It's been a pleasure.
Thank you, sir, for joining us today.
Thank you. I'll sign off now.
We had wonderful time, sir, today. We will remember your